Section 8.3, Polar Coordinates. Polar coordinate system is another way to represent points on a plane. The polar coordinates are points labeled in the form of r theta and plotted on the polar grid. Before we talk about the significance of r and theta, we'll start by talking about the anatomy of the polar grid. The pole of the polar grid coincides with the origin of the rectangular coordinate system. So we can think of the pole as the center of our polar coordinate system. The polar axis coincides with the positive x-axis of the rectangular coordinate system. The first component of our polar coordinates is r. R is the radius or length of the directed line segment from the pole. We'll talk more about what we mean by directed line segment later, and it ties in with the warning that r can be negative. Theta is an angle measured in radians that indicates the direction of r, and theta is our angle drawn in standard position. Recall that angles drawn in standard position have their initial side along the positive x-axis, which we call the polar axis. So here, using the proper terminology, the initial side of all of our angles will be drawn so that way the initial side coincides with our polar axis. Recall that theta can be a negative angle. Negative angles indicate a clockwise rotation, while positive angles still indicate a counterclockwise rotation. Now let's take a look at an example of a few points plotted on our grid. The point 3 pi over 3 means that we're on the direction of pi over 3 radians, which we can see the terminal side of which drawn in blue. And the positive 3 means we are 3 units away from our pole in the direction of the terminal side of pi over 3. As we can see drawn on our plane, since it's on the circle that has a radius of 3. Next, for the 4 negative pi over 6, since our angle is negative, that means we rotated clockwise to obtain the standard position of negative pi over 6, which would have a terminal side highlighted in blue. Since r is positive 4, then our point is 4 units away from the pole in the direction of the terminal side of negative pi over 6. And you can see that we are 4 units away since we are on the circle with radius 4. Last, we'll talk about the point negative 2 pi over 6. This is where we have to be careful with the sign of r. Recall that r is the length of the directed line segment. Here's where the term directed comes into play. The terminal side of pi over 6 would be located along the line that I have highlighted in red. Because our radius is negative, we're actually going to go in the opposite direction of our terminal side. So I'll extend our terminal side in the opposite direction, and we'll plot our points 2 units away along the opposite side of our terminal side, as indicated by our point that we have plotted for negative 2 pi over 6. And this is where the rectangular line segment comes into play. When our r is positive, we are going in the same direction of our terminal side of our angle. However, if our r is negative, we go in the opposite direction of our terminal side of our angle. Next, we're going to practice plotting some points on the polar grid. We'll start by plotting 2 pi over 2, and we'll plot our point in red. The angle pi over 2 would coincide with the positive y-axis in our rectangular coordinate system. Since our r is positive, we'll be traveling along this terminal side, and we'll be 2 units away from our pole, which will be located at the indicated point. So there's our point for 2 pi over 2. Next, we'll graph 3, 4 pi over 3 in blue. Just like before, we do want to locate the angle 4 pi over 3, which will be there in blue. R is positive 3, so we want to be 3 units away from the pole along our terminal side, which will be located there. So there's our point, 3, 4 pi over 3. Next, we'll plot the point 1, 7 pi over 6. We'll start by locating 7 pi over 6 on our polar grid. 7 pi over 6 would be located there in green. Since r is 1, we will be going in the direction of our terminal side, 1 unit away from the pole. So there's our point for 1, 7 pi over 6. Next, we'll plot 4 pi. Pi would be located along our negative x-axis indicated in orange. Since our r is positive 4, we are going in the direction of our terminal side, 4 units away from our center. And there's our point in orange. Now we're going to plot negative 2, 3 pi over 2. We'll start by drawing 3 pi over 2 in standard position, and that would coincide with the negative y-axis. However, our radius is negative this time. That means we're not going in the direction of our terminal side. We'll be going in the opposite direction. So instead of going down, we're going up 2 units away from our pole. And there's our point for negative 2, 3 pi over 2. Next, we'll plot 3, negative 2 pi over 3. Negative 2 pi over 3 means we're rotating clockwise 2 pi over 3 radians, which would be located along the blue line that I just drawn. Since our r is positive 3, that means we're 3 units away from the pole in the same direction as the negative 2 pi over 3, which would be located there. And there's our point for 3, negative 2 pi over 3. Next, negative 1, negative 11 pi over 6. We'll start by locating negative 11 pi over 6. Negative 11 pi over 6 is a rotation clockwise by 11 pi over 6 radians, which will place us along this green line. However, our radius is negative 1, which means we're going in the opposite direction of our terminal side of negative 11 pi over 6. So extend our line segment in the opposite direction, and we're going 1 unit in the opposite direction of our terminal side, which would place us there. And there's the location of negative 1, negative 11 pi over 6. Last, 4, 5 pi. 5 pi radians is 2 full rotations around the circle with an extra pi radians left to go, which will place us on the negative x-axis. Since our r is positive 4, then we're traveling 4 units away from our pole in the direction of 5 pi, which would place us there. So there is our location of 4, 5 pi. Observe how 2 pi over 12 and negative 2, 3 pi over 2 were in the same position. Same thing goes for each of these pair of points. This was not a coincidence. Turns out there are multiple ways to represent the same point in polar coordinates. So as we've seen in the last example, one of the major drawbacks of the polar coordinate system is that there are many ways to represent the same point. However, in the rectangular coordinate system, the representation is unique. The multiple ways of representing a point boil down to the fact that we have coterminal angles, along with the fact that we have r potentially being positive or negative. It often helps to alter the representation of a point to make it more convenient to work with. The way we can alter points are the following. Negative r theta equals r theta plus pi. If our r is negative, we can make r positive by adding pi to our angle. The second way we can alter the representation is based off of coterminal angles. R theta is equal to r theta plus 2 pi n, where n is an integer. So if theta is too big or too small, we can subtract or add multiples of 2 pi to make the angle fit between 0 and 2 pi, or whatever conditions we wish. So if we take a look at our next example, we're going to find the polar coordinates of the point -2, -pi/4 that satisfy each of the following conditions. First, we want r to be positive and theta to be between 0 and 2 pi. Currently, r is negative. Well, thanks to what we discussed above, I can change the sign of r, but in doing so, I have to add pi to my angle. So -2 -pi/4 is equal to 2 -pi/4 plus pi, which is equal to 2 3pi/4. So checking to make sure our points meet our conditions, r is positive and 3pi/4 is between 0 and 2 pi. So that is the representation we're seeking. So -2 -pi/4 is equal to the point 2 3pi/4, which does satisfy our given conditions. Next, we're going to rewrite our point so that way our r is positive and theta is between -2 pi and 0. We've already seen in the previous example that -2 -pi/4 is equal to 2 3pi/4. So our r is positive, but now let's rewrite it so that way theta is between -2 pi and 0. Right now, our angle is too big. Well, thanks to coterminal angles, I can subtract 2 pi from my angle to make it smaller. And we subtract 2 pi from our angle, we get that our point -2 -pi/4 is equal to 2 5pi/4. R is positive, -5pi/4 is between -2 pi and 0, so that is the representation we seek. Next, we're going to rewrite our point so that way r is negative and theta is between 0 and 2 pi. Since our point already starts with a negative r, our first condition is already satisfied. However, our second condition is that theta has to be between 0 and 2 pi. Currently, the -pi/4 is too small. So we're going to add 2 pi to our angle, and when we do, we get -2 7pi/4. Checking to make sure our conditions are satisfied, -2 is negative, 7pi/4 is between 0 and 2 pi. So -2 7pi/4 can also represent the point -2 -pi/4, satisfying the given conditions. Next, we're going to plot the point -2 pi/4 on our polar grid. Thanks to our previous exercise, we have 4 ways to represent the same point. So we can use either one of these 4 representations to plot our point. Typically, the easiest points to plot are the ones where r is positive. Since whenever r is positive, we're going in the direction of the terminal side of our angle, drawn in standard position. So I would either want to use the 2 3pi/4 or the 2 -5pi/4 representation. However, we're probably more comfortable with positive angles since we work with positive angles more. So we'll use the representation 2 3pi/4 since r is positive and theta is positive. The terminal side of 3pi/4 would be located halfway between the terminal sides of pi/2 and pi. Since our r is 2, we are 2 units away from the pole, which would be located there. So even though we plotted the point for 2 3pi/4, since that is equivalent to -2 -pi/4, then the point we have currently in blue would be our point -2 -pi/4. So keep in mind, thanks to the above ways of altering the representation of a point, we can always rewrite our point so that way r is positive, and our theta is a value that we're comfortable with plotting in standard position. So it's highly suggested that if you don't like the representation of the point and you're finding it too difficult to plot, rewrite it using positive r's and angles that we can easily plot in standard position. Even though we just talked about the drawbacks of the polar coordinate system, there are still many benefits. Before we talk about the benefits, let's take a look at how we can convert between polar and rectangular coordinates. Whether we have a point represented in rectangular coordinates x, y, or r theta, we're going to have the following relationships. The first two are x equals r cosine theta and y equals r sine theta. This comes from the fact that in the rectangular coordinate system, x and y represent the horizontal and vertical distance from the origin to the point, while r represents the straight line distance between the origin and the point. So r, x, and y form a right triangle. And from this right triangle, and theta would lie here between the straight line distance of our point and the origin or pole, or polar axis, or positive x-axis. With respect to theta, y would be the opposite side, x would be the adjacent side, r would be the hypotenuse. So we would have, thanks to our trig ratios, cosine theta equals x over r, and sine theta equals y over r. And if we multiply both sides by r, that's how we obtain the formulas x equals r cosine theta and y equals r sine theta. We often use these two formulas to help us convert points from the polar system to the rectangular system. 2 other formulas we can come up with from this diagram is r squared equals x squared plus y squared. This comes directly from Pythagorean theorem, since r is the hypotenuse and x and y are the legs of the triangle. The second tangent theta equals y over x. This just comes from the definition of our trig functions with a right triangle. However, be very careful using the tangent theta equals y over x. If you were to apply inverse tangent to both sides, that would only give you angles in quadrants 1 and 4. However, our points may be located in quadrants 2 and 3. So make sure you are paying attention to what quadrant the point is located in. That way you can find the appropriate angle theta. Both of these last two formulas are typically used to convert points from rectangular to polar coordinates. All four will be used when we're trying to convert entire equations from polar to rectangular. Now we're going to convert each of the following points from rectangular coordinates to polar coordinates, where the r is positive and theta is between 0 and 2 pi. We'll start off by finding r by using the formula r squared equals x squared plus y squared. So taking 2 and 2, plugging in for x and y respectively, we get that r squared equals 2 squared plus 2 squared, which means r squared equals 8. From there, we'll take the square root of both sides, and we get r equals plus or minus 2 root 2. However, we want r to be positive. When we restrict r to being positive, we do not need to write the plus or minus, because our answer for r will always be positive in this case. So r is just 2 root 2. As for theta, we're going to use the relationship that tangent theta equals y over x. So tangent theta will equal 2 over 2. In other words, tangent theta will equal 1. Well, in general, there's two possible angles on the unit circle that cause tangent to equal 1. Since our point 2, 2 is in quadrant 1, we want to find the angle theta that is in quadrant 1, where tangent of that angle will be 1. If we look through the unit circle, we would get that theta would be pi over 4. So our point 2, 2 is equivalent to 2 root 2 pi over 4. Next, we'll take a look at the point 4, negative 4 root 3. We'll start off by finding r. R squared would equal 4 squared plus negative 4 root 3 squared. So r squared equals 64, square root. And since we know from our restriction that r is positive, we get r equals 8. Now to find theta, tangent theta would equal negative 4 root 3 over 4, which means tangent theta would equal negative root 3. Now we need to check which quadrant our point is in. Our point would be in quadrant 4. If we look at quadrant 4 for a point on the unit circle where y divided by x is negative root 3, we get that theta would be 5 pi over 3. So our point for negative 4 root 3 in rectangular coordinate system is equivalent to 8 5 pi over 3 in the polar coordinate system. Next, we're going to convert the point negative 3, 3 to polar coordinates. Just like before, we'll start by finding r. So here, r squared would equal negative 3 squared plus 3 squared, which means r squared equals 18. And because r is positive, you'd have r equals 3 root 2. Next, we'll find our angle. Tangent theta would equal 3 over negative 3, which means tangent theta equals negative 1. Now from there, we need to think about what quadrant our point is located. Our point negative 3, 3 would be located in quadrant 2. So we're looking for an angle in quadrant 2 such that tangent of theta equals negative 1. Looking through our unit circle, we can see that theta is 3 pi over 4. So the point negative 3, 3 in rectangular coordinates is the point 3 root 2, 3 pi over 4 in polar coordinates. Last, we'll convert negative 2 root 3, negative 2 to polar coordinates. Just like before, we'll find r, and through the same process we've used so far, we get that r equals 4. Next for theta, tangent theta would be negative 2 over negative 2 root 3, which means tangent theta equals root 3 over 3. Now thinking about what quadrant our point's in, our point would be located in quadrant 3. So we want to look for an angle in quadrant 3 where tangent of that angle is root 3 over 3. And after looking through the unit circle, we get that theta would have to be 7 pi over 6. So negative 2 root 3 negative 2 is equivalent to 4 7 pi over 6. Make sure you are paying attention very carefully to what quadrant your point is located in. Do not just apply tangent inverse without thinking about where your point is located. Remember, tangent inverse only gives you angles in the first and fourth quadrant. So you want to try to look for the solutions that are in the proper quadrant based off of where the point is located. Now we're going to convert each of the following points that are in polar form to rectangular. To do this, we're going to use the formulas that x equals r cosine theta and y equals r sine theta. Here r is 2, theta is pi over 2. So x would be 2 cosine pi over 2, y would be 2 sine pi over 2, which means x would be 0 and y would be 2. So in rectangular coordinates, 2 pi over 2 is the same as 0, 2. Next, we'll convert negative 2, 5 pi over 4 from polar to rectangular. Just like before, we'll use the formulas above. So x is negative 2 times cosine 5 pi over 4, which is root 2. And y is negative 2 sine 5 pi over 4, which is also root 2. So our point negative 2, 5 pi over 4 is equivalent to root 2 in rectangular coordinates. Next, we'll convert the point 1, 7 pi over 6 using our formulas from before. X would equal 1 times cosine 7 pi over 6, which is negative root 3 over 2. Y would equal 1 times sine 7 pi over 6, which is negative 1/2. So our point 1, 7 pi over 6 in polar coordinates is equivalent to negative root 3 over 2, negative 1/2 in rectangular coordinates. Next, we'll convert the point 3, 5 pi over 3 from polar to rectangular. x is equal to 3 cosine 5 pi over 3, which would equal 3 halves. Y would equal 3 sine 5 pi over 3, which is negative 3 root 3 over 2. So our point is equivalent to 3 over 2, negative 3 root 3 over 2 in rectangular coordinates. Now we're going to convert the following equations from rectangular to polar. To help us, we're going to use the formulas that we saw in the previous slides that allowed us to convert from polar points to rectangular points or vice versa. The two formulas that allowed us to convert from polar to rectangular points was x equals r cosine theta and y equals r sine theta. We're also going to try to use r squared equals x squared plus y squared as well to help us not have to worry about the Pythagorean identity so much. With these formulas in mind, let's take a look at rewriting x equals 5. To rewrite in the polar coordinates, we're going to replace the x that we see here with r cosine theta. Now, typically when we write our equations in polar form, we do want to try to isolate r. So we can divide both sides by cosine theta, which means r equals 5 secant theta. Next, x squared plus y squared equals 6y. Now, I could replace the x and the y on the left-hand side with the r cosine theta and the r sine theta. However, there's a quicker way to rewrite that left-hand side. From our formulas, we know that x squared plus y squared is r squared. Our right-hand side will replace the y with the r sine theta, and we have that r squared equals 6r sine theta. Now, we could have replaced x and y with r cosine theta and r sine theta respectively on the left-hand side, factor out the r squared, and then use the Pythagorean identity to add the cosine squared and the sine squared, which would still leave us with r squared. So while yes, I could have replaced the x and the y on the left-hand side, using the fact that r squared equals x squared plus y squared is a lot faster. To finish making this version as compact as we can, we're going to divide both sides by r, and we get r equals 6 sine theta. Next, we're going to rewrite x squared plus y plus 4 quantity squared equals 16. As stated before, I could replace the x and y's now, but I noticed the x squared, so let's try to expand the y plus 4 squared and see if we get a y squared to make the replacement a little bit faster. Y plus 4 squared is y squared plus 8y plus 16. One thing I noticed is a 16 on both sides, so we can go ahead and cancel out the 16 by subtracting 16 from both sides. I now see the x squared plus y squared, which we know equals r squared, and I can replace the y with r sine theta. So we get r squared plus 8r sine theta equals 0, which means r squared equals negative 8r sine theta. And if we divide both sides by r, we get r equals negative 8 sine theta. Next, we're going to rewrite the 2x squared plus 3x equals y minus 2y squared. I do notice an x squared and a y squared, one on each side of the equation. So this makes me want to try to use the fact that r squared equals x squared plus y squared. To set up for that, we'll start off by adding 2y squared to both sides. And while we're at it, we'll go ahead and subtract 3x. The reason why I'm subtracting 3x, I'll explain why in a little bit. And we get that 2x squared plus 2y squared equals y minus 3x. On the left-hand side, let's factor out the 2 since that's a common factor. And we have 2x squared plus y squared equals y minus 3x. On the left-hand side, we see the x squared plus y squared, which we can replace with r squared. On the right-hand side, we'll replace the y and the x with r sine theta and r cosine theta respectively. And we can see that our thetas are all on the right-hand side. And this is why I moved the 3x to the right-hand side earlier. I knew that the x would be replaced with the r cosine theta and the y would be replaced with the r sine theta. Since we're trying to isolate r, it helps to get all of our thetas on one side. And if you know a term is going to be converted to an expression in terms of theta, it helps to move it over so that way they're all on one side preemptively. Notice how r is a common factor. So we'll factor r out on the right-hand side. Then we can cancel out an r by dividing each side by r. And then we can divide by 2 to isolate r. And we get r equals sine theta minus 3 cosine theta all over 2. Now we'll discuss one of the benefits of polar coordinates. One of the benefits of polar coordinates is it can make some equations that are very complicated in the rectangular coordinate system much simpler and easy to work with. For example, one equation that we converted from rectangular to polar was x squared plus y squared equals 6y. If we graph that into Desmos, we can see that makes a circle. And in the rectangular coordinate system, this would not be a function, since it would fail the vertical line test. This makes calculus operations very difficult to deal with, especially an operation called integration. Also, notice how many operations there are. There are 2 squares, addition, and on the other side, multiplication. When we convert to polar coordinates, we got r equals 6 sine theta. In order to see the polar grid, click on the graph settings up on the top right, and you can select between the rectangular grid here on the left or the polar grid here on the right. And there you can see the polar grid and r equals sine theta in blue. Notice that both graphs are identical. Both graphs are identical because both equations represent the same thing, just written in different coordinate systems. But r equals 6 sine theta would be much easier to work with since A, r is a function of theta. And keep in mind, since this is a different coordinate system, the vertical line test doesn't tell us anything here because the vertical line test only works in rectangular coordinates. So while y is not a function of x in the first equation, r is a function of theta in the second equation, and functions are easier to work with. Second, because of how sleek and compact the polar version of our equation is, it does make it much easier to work with in calculus, especially when we're using the operation known as integration. If we go back and check all of our results from the previous problem, our equations in rectangular coordinates were not functions. But when we converted them to polar, they were functions. R was a function of theta. So in some cases, we can rewrite equations that are not functions in the rectangular coordinate system into functions of the polar system. Next, we're going to convert each of the following equations that are in polar form to rectangular form. Now, I've written the x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared that we used in the previous example. But I've also went ahead and rewrote the tangent theta equals y over x because we may use that from time to time when theta is isolated. There's a few different tricks that we can use to convert from polar to rectangular. If we take a look at the first equation, r equals 5, ideally, I would like to see x squared equals a number. Since r is constant here, the trick to this one is we're going to square both sides of the equation, and that gives us r squared equals 25. Now that I have the r squared, I can replace that with the x squared plus y squared. So the rectangular version of r equals 5 is x squared plus y squared equals 25. Next, for theta equals 5 pi over 4, since theta is isolated, we can apply the tangent function to both sides of the equation. Tangent theta is y over x in rectangular form. Tangent of 5 pi over 4 is positive 1. So we have y over x equals 1, multiply both sides by x to make the equation look nicer, and we get y equals x. So theta equals 5 pi over 4 in polar version is equivalent to y equals x in rectangular. Next, we're going to convert r equals 1 over 1 minus sine theta. One thing to be aware of is in our formulas, we have r cosine theta and r sine theta. So I always want to try to manipulate and maneuver my equation so that way I see r sine theta and r cosine theta to be able to replace them with x and y. If we take a look at what we have so far, the first thing we can do is go ahead and clear those fractions. And when we multiply both sides by 1 minus 2 sine theta, we get r times 1 minus 2 sine theta equals 1. Then we can distribute in the r, and we get r minus 2r sine theta equals 1. I'm happy about the r sine theta, but the other term just being r is a little bit of an issue. So let's go ahead and add the 2r sine theta to the other side. And we get r equals 1 plus 2r sine theta. Well, very similar to the first problem, I want to see r squared, so that way I can replace it with x squared plus y squared. So we can square both sides of the equation, and when we do, we have everything we need to convert nicely. The r squared becomes x squared plus y squared. The 1 plus 2r sine theta becomes 1 plus 2y. So we have x squared plus y squared equals 1 plus 2y quantity squared. For the next problem, we're going to convert r equals to cosecant theta. We're used to sine and cosine in our polar form, so let's go ahead and use the reciprocal property to rewrite the cosecant theta. And when we do, we get r equals 2 sine theta. Just like in the above example, I do want to see r sine theta since I know that's y. So we can multiply both sides by sine theta to clear the denominators, and we get r sine theta equals 2. R sine theta becomes y. Our right-hand side will stay 2. So r2 cosecant theta is equivalent to y equals 2. Next, we'll get to some more challenging problems. First, r equals sine of 2 theta. The first thing that makes this problem a little bit more challenging is the 2 theta. All of our conversions use theta, r cosine theta, r sine theta, not sine 2 theta. So what we're going to do here is we're going to rewrite the sine 2 theta using our double angle formula. So r is equal to 2 sine theta cosine theta. Now I want to get r sine theta and r cosine theta. To help me achieve this, I'm going to multiply both sides of my equation by r squared, or r times r. My left-hand side will be r cubed. My right-hand side, because I want r sine theta and r cosine theta, I'll rearrange my 5 factors and rearrange them as 2 r sine theta, r cosine theta. On my right-hand side, I have everything I need to replace the r sine theta and r cosine theta with x and y. But I still have a problem with the r cubed. Because x squared plus y squared equals r squared, I want r to have an even power. So similar to what we've done before, we're going to square both sides of the equation. And the r cubed squared, because I want r squared, I'm just going to switch the powers. R cubed squared is equivalent to r squared cubed, thanks to power to a power. And for the right-hand side, we'll keep it as is for now. Now we can do our replacements. R squared becomes x squared plus y squared. 2r sine theta, r cosine theta becomes 2yx. The left-hand side we'll keep as is. And on our right-hand side, we'll go ahead and square everything, giving us 4x squared y squared on the right-hand side. So we have x squared plus y squared quantity cubed equals 4x squared y squared is equivalent to r sine of 2 theta. Next, we're going to rewrite 4r squared sine squared 3 theta plus 4r squared cosine squared 3 theta equals 5. Now, it may seem tempting to replace the r squared sine squared 3 theta and r squared cosine squared 3 theta with y squared and x squared right away. But we do have to be a little careful because our angles are 3 theta, not theta. But if we observe, our left-hand side can be simplified. 4r squared is a common factor, so we can factor out the 4r squared sine squared 3 theta plus cosine squared 3 theta, thanks to the Pythagorean identity, is equal to 1. And anything times 1 is itself. So to isolate the r squared, we'll divide by 4, and we get r squared equals 5 over 4. So our original equation, still in polar form, can be simplified down to r squared equals 5 over 4. Then we can replace our r squared with x squared plus y squared. So 4r squared sine squared theta plus 4r squared cosine squared 3 theta equals 5. in polar form is equivalent to x squared plus y squared equals 5/4 in rectangular form.